Welcome to Empowered Learning. This particular video will be about the intermediate value theorem, what that theorem is actually trying to communicate to us, and how do we use that particular theorem to prove the existence of solutions. Let's first start with what the intermediate value theorem actually says. Suppose that f is continuous on some closed interval, a, b, where a and b are real numbers. And so we are assuming here that this closed interval, we're talking about x values. Also, let n be some real number, so that's what this means. Let n belong to the real number set, be any number between f of a and f of b. Now notice that if we're referring to a and b as x values, then f of a and f of b would be corresponding y values. And so we're looking at this number n to be in between these two y values here. If we're looking at the corresponding x values to that within this closed interval from a to b. And we're looking at that such that f of a and f of b aren't equal to one another. So in other words, we do not want the endpoints of whatever open interval that we're talking about here to be the same. Then there exists at least one number, so that's what this backwards e means. There exists at least one number c that belongs to the open interval of the x values from a to b, meaning c is strictly in between a and b, such that f of c is equal to n. Or put another way, we know that there is a point c n on the graph of the function f of x. Okay? So if I read that all again and try to interpret it, it says, let f be a continuous function on a closed interval. That means a function that has no holes, gaps, jump discontinuities, breaks, anything like that. So we know that f is going to be continuous on some closed interval of x values. And we also know that we're considering a y value that's in between the f of a and the f of b. If we have that situation, or if we have that environment, then we know that essentially that environment guarantees us to be able to have a solution to the equation f of c is equal to n if c is a value strictly in between a and b. Okay. Now the translation that I have written here below is a little bit more involved, and I'll go ahead and read that. So it says, if f is continuous and a non-constant function for every real number over the given x value interval from a to b, then every x value in the open interval a to b has a corresponding y value in the open interval f of a to f of b. In other words, we can guarantee a solution to the equation f of c is equal to n, or like how I said before, we know that we have a point c n that's going to be on the graph of this function as long as these following conditions are met. Number one, f is continuous and non-constant on this closed interval. We have some value c, x value that we pick strictly in between a and b. And of course, n is a value that is strictly in between f of a and f of b. Okay, and we know that f of a and f of b are not equal, and so that's the point of that non-constant function point. Okay, so if we look here at figure X, we'll see that we actually have a graphical interpretation of exactly what we're talking about here. So notice here that first thing that we see is that we have closed interval a to b. We see that we've picked some values c that are strictly in between a and b. We have a y value, which we're calling n, that is strictly in between the interval from f of a to f of b. And of course, f of a and f of b are the corresponding y values for the x values a and b respectively. Okay, and you see that our function here has no holes, no breaks, no gaps, no jump discontinuities, or anything like that. So because of that, we know that the intermediate value theorem guarantees us at least one solution to f of c equals n. Or put another way, we know that we have at least one point Cn on this graph. Okay? In this case, you see that because of the type of function I have, it is actually, we actually have three values of c that are strictly in between a and b for where that happens. Okay? Now, in the world of mathematics, what the intermediate value theorem is actually an existential theorem or existential theorem, depending upon how you want to say the word. But basically, what this theorem does, it says, hey, if you have this sort of environment, we know that you have a solution to this equation. It just tells you that it's out there. It does not tell you exactly how to get the exact solution. It doesn't tell you what the solution is. It just says that if you have these conditions or this environment, if you want to go looking for that solution, it will be out there. Now, you have to look at other things as far as how to actually find that solution, but at least you won't be wasting your time going out there to look for it, because the conditions are such that that solution for whatever it is that you're looking for will be out there. Okay, so that's how the intermediate value theorem is used. An example of how the intermediate value theorem is sort of a foundation for a lot of the things that we do is if we look at this function here, y equals x squared minus 2. Then, of course, if I ask you to find the x-intercepts for this function, then what you're really asking me to do is this, okay? But it's because of the intermediate value theorem that we know that this particular solution even exists in the first place, okay? Now, if I was to go and look for the solutions for the x-intercepts for this, we know that the environment for the intermediate value theorem here is such that it's not going to meet all the conditions to be able to solve this. And that's why in this case, we know that for x squared plus 2, there will not be any real number solutions to it. Or put another way, there won't be any x-intercepts for that. But of course, those conditions actually do meet the criteria for the function x squared minus 2 for that to happen. Okay. All right, so let's go ahead and move on here. So what I want to do now is give an alternative version of the intermediate value theorem, and we use this particular version of it strictly for polynomials. And so the reason for that is with polynomials, we know that polynomials are smooth and continuous functions for all the real numbers. So its domain is all real numbers. So by doing that, it makes it easier for us to be able to figure out, will a particular function meet the conditions for the existence of a solution. So this one starts off by saying if f is a polynomial and c is an x value strictly in between the x values a and b, and n is strictly in between the y values f of a and f of b, where f of a and f of b aren't the same, then we know that we have a guaranteed solution, f of c is equal to n. But if we rewrite that another way, then we can look at it as f of c minus n is equal to 0. And so thus, if f of a and f of b are of different sign, meaning one of them is positive and the other one is negative, we can conclude that there exists at least one solution for this particular equation here. Okay. Or put another way, c is a 0 or an x-intercept of the function f of x minus n. Okay. Now, sounds real difficult, but all that we're really saying is this. If the function that we're dealing with is a polynomial, and I have a closed interval of x values that I want to look at this function within, so I just want to focus on that part. if I want to figure out, does this particular function have a particular point at x equals c, which would be strictly in between there, one way that I can do it is say, all right, well, instead of looking at my function f of x, let's look at my function f of x minus n and figure out, all right, well, is the function going to have an x-intercept there? And if I know that f of a, which is the corresponding y value for a, has different sign than f of b, then what happened was something like this. So let's say this is f of b, this is f of a, this is a, that's b, and this is some c here. So if my function kind of looks like this, then I know that if f of b was positive and f of a was negative, then somewhere in between x equals a and x equals b, my function had to cross the x-axis. Okay? And so that's another way of me looking at the equivalent statement of saying, hey, if I have a function that is continuous for all values of x strictly in between a and b, then I know that I have a solution to f of c, or put another way, the point Cn is actually on the graph. So let's look at an example of how this is actually applied. So here we say let f of x be x squared minus 2. And we want to determine if f of x has a 0 between these x values here. So in terms of the intermediate value theorem, this is your a, that's your b. And of course, when we go and calculate f of a and f of b, then of course this one is positive, that one is negative. And so we see that for x squared minus 2, somewhere in between x equals negative 3 and x equals negative 1, this graph crossed the x-axis. So I know by the intermediate value theorem, it guarantees me that I have an x-intercept somewhere in between negative 3 and negative 1. Okay? Doesn't tell me exactly what it is, but it tells me that whatever it is going to be in between those two x values. Okay? Now, of course, we know other methods for finding the 0 in between here. Of course, we can just add 2 to both sides and then take the principal root of both sides, and we see that the one that we're talking about here is the negative square root of 2. So this is the actual process for finding the solution. But of course, we wouldn't be able to do the process unless we knew that the conditions were set up, or the conditions were made so that we could actually find out what the solution would be in the first place. Okay. All right, so let's look at some other examples of how we could possibly find or possibly use the intermediate value theorem to help us find the existence of solutions to an equation. So we have the function f of x is equal to x squared plus 10x. And what we want to do is show that there is indeed a real number c such that f of c is 1000. Okay. Now, how we're going to go about doing this is we need to first look at the function f of x itself. Okay. And so f of x is comprised of two separate functions, which is x squared and 10 times sine x. Now, we know that x squared is going to be continuous for all real numbers. Okay, and this is just for all, didn't write that symbol correctly. So for all x, that's a member of the real numbers. We also know the same thing is true for 10 sine x. And we know it is also continuous for all values of x within the real numbers. So that implies that f of x is going to be continuous for all values of x within the real numbers. So we know that part. Now what we have to do is make sure that we know we identify some A and some B, so that when we map to f of A and f of B, that we know that the value n that we're going to select, and in this case our n would be 1000. N would be strictly in between f of A and f of B. Okay. So the quickest way to do this is, we know that function is continuous. So because of that, we also know that it's continuous for all real numbers. So we're definitely going to have some f of A and f of B to where this would work. So in seeing that, we could go ahead and just look at a table and figure out a range of x values to where this would be in between. And so I'm going to do it to 1 decimal place. So what you could do is just grab your calculator and type in this function, x squared plus 10 times sine x, and start to play around with the numbers until you get to something that is very close to 1000 for the y value. So just sort of playing around with different numbers with our calculator here. I'm just going to list several values of x and figure out what the corresponding y value would be, and sort of telescope my way to figuring out what that answer would be. So if we go look at this, let's say I want to figure what this is when x is 10. So when x is 10, I get a value that is approximately 94.6. So of course I got a long way to go. So let me see if I can go to x is 30. So when x is 30, I have approximately 890.1. So let's see if I go to 40. So if I go to 40, it's way over. Okay, it's approximately 1607.5. So I need to go back down. So let's say if I go to, let's say 31. So if I do that, I'll get approximately 9,000, sorry, not 9,000, 956.95, which is approximately 957. So we know we're getting close there. If I go to 32, then I see that now I'm at 1029.51. So here we definitely know that this value C is going to be in between 31 and 32. So if we were fine with that, we could say that A and B, we can guarantee a solution for f of C is equal to 2000, where C is going to be strictly in between 31 and 32. We could say that. If we wanted to get more precise, we could just keep on looking. And so if we keep on looking, you'll let's say if I went to 31.6. So 31.6 gives me 1000.394. So that's 0.4. So that's really close. So if I look at 31.5, that gives me 993.08794. So as you can see here, I could also say, if I wanted to be more accurate, that C is a value strictly in between 31.5 and 31.6. So it really just depends upon how accurate you want to get, or how tight you want that closed interval to be. But at the end of the day, we know that since the function f, both parts of it were continuous for all real numbers, and as you see here, we have a situation where the f of A, which is, let's say in this case, this is the f of A, this is the f of B, this is the A, that's the B, and of course f of A and f of B are not the same, and this is not a constant function here. We know that the environment is set up to where we can guarantee you that there is a solution to this equation, f of c is equal to 1,000. Even though we don't know exactly what it is, we may not have a way to exactly solve for it, but we know that it is out there, okay? And so that is the purpose of the intermediate value theorem, to show you those things. So let's go ahead and move on to a more practical example. Okay, so for this example, what we want to do is use the intermediate value theorem to show that there is a root of this equation here. And what I've done here on the side is actually draw what this equation is trying to communicate to us. And so we see that we have cube root of x is equal to 1 minus x. So if we interpret this equation, it's trying to figure out for what values of x does the graph of cube root of x and the line 1 minus x intersect each other. And of course, we see that here. Now, notice that the way that this looks, we could take this equation and actually turn it into a polynomial equation. Okay, and also notice here that because of where this point is on the graph, and this is our value c, you notice how this is in between 0 and 1. So what we could possibly say is let a equal 0 and let b equal 1. And then what we could do is set up everything else. So we want to figure out what a f of 0 is, and we want to figure out what a f of 1 is. Okay? And then from there, we see that both functions, cube root of x and 1 minus x, are continuous for all real numbers. So, of course, the difference in between them would also be continuous for all real numbers. So here we have a situation where we could actually use the intermediate value theorem, provided that f of 0 and f of 1 won't be the same value. Now, an easy way to do this is we could, instead of doing that first, let's just take the cube of both sides. So that would be an easy way to do this. So if we do that, then of course here that would just be x on this side, and this would be 1 minus x cubed on that side. Now we could multiply this out if we wanted to, but there's really no need. We know that this is going to be a polynomial of degree 3 on this side. If we were to subtract both sides by 1 minus x cubed, it would look like this. And then that would be 0. This is going to be a polynomial. So even though it is not written in the traditional canonical form, we do know that it's going to be a polynomial. And so because of that, we now have a situation where we can let f of x equals this situation here. And so now that we have that, we know that it's a polynomial. We can actually use the alternative form that I've stated earlier of the intermediate value theorem. So we just need to see if there's a sign change in between x equals a and x equals b. So in looking here, if we want to figure out what f of 0 is, we just plug in 0 for this function here, and we'll see that we get -1 for an answer there. If we evaluate the function f at 1, then you'll see that all this ends up being 0, and that is a positive 1. And so now, since we have a sign change going from f of 0, at x equals 0 to x equals 1, then by the intermediate value theorem, we can conclude that there is a solution, or there is a root to this equation here. And so we'll state it like this. So then by intermediate value theorem, we know that this has at least one solution. Thus, the equation, and then we'll just write out what that equation was. Also has at least one root. And so that's how we would use the intermediate value theorem to show that, hey, there is some solution that actually exists out there. Now, of course, again, we didn't go through the whole thing of trying to find out exactly what it was, because that's not the purpose of the intermediate value theorem. The purpose of that theorem is to show you that, hey, we have the conditions available so that we can actually figure out what that actual value is. And of course, depending upon what you're working on, there are other methods to make that happen. But you just need to know that it is out there before you even start to look for it. Okay? And so with this last example, we'll go ahead and conclude the video on intermediate value theorem. I hope this sort of clears up why the intermediate value theorem is important, as well as some of the ways that we use it. So hope this helps. Take care.